inStem and CDAN. Please look them up because they're very long and wordy. So today really is a celebration of sorts. We're really happy to have Arjun, who is a researcher at inStem, and he's going to be talking to us about stem cell injury repair using stem cells. And I'm really happy that all of you could come, and we'd like to celebrate 1 year with you. So your being here is particularly special to us. So I just want to say thank you very much, Arjun, for agreeing to speak today, and all of you for being here.
Hi, good morning. My name is Arjun, and as Mahin said, I'm at the Institute for Stem Cell Science and Regenerative Medicine.
Arjun, can we have a mic for you?
Yeah.
Will not be audible back here?
This is the first time in my life I've been told that I'm soft-spoken. Oh, never too late. I think my fellows this cluster that these are the members of the lab that I run at the inStem. Ours is a lab that tries to understand mechanisms for lung injury repair. More importantly, we try to understand how the lung copes with a whole bunch of environmental insults, ranging from chemical poisons to infectious agents like tuberculosis and so on and so forth. So when Mahin spoke to me and asked me to speak at this session, the question was, what is it that I should speak to you about that would be of interest to the both of us? And given that my lab is fundamentally interested in the mechanisms of injury repair, and given that there is a wider interest in what stem cells are and what they can do, I thought that we could have a discussion about what stem cells are. So what I'm going to share with you is my perspective on what stem cells are and what value they are to us from the standpoint of the kind of medical problems that we face today.
I'm going to interrupt again. And one thing that I forgot to mention is that the model of Science Cafe is an extremely relaxed, casual exchange of knowledge. So this is not supposed to be a lecture. You're very welcome to interrupt Arjun at any point in time, ask any questions about anything from stem cells to rare devices, shoes, to anything you want. This is supposed to be a conversation, it's a dialogue. So please just be comfortable, treat this like your living room, and be comfortable, and please bombard the speaker the way you like.
Yeah, absolutely. Please feel free to stop me at any time. I'm not, so one of the concerns that we have when we come in, so to speak about science in a general setting like this is how technical should we get? And I think that we are all intelligent people, and I think that if one is to describe the preliminary or the primary data in its utmost clarity, that anybody who is able to think rationally should be able to understand it. And so I'm not at any level going to try and hold back. And the evidence that I'm going to show you in support of some of the ideas that I present are in fact going to be the data from the experiments themselves. So if you don't understand it or you need some help in working through the data, please let me know and I'll be happy to go through it. So let me start by giving you what is an outline for this presentation or this discussion, so that you know what's coming. So the first part of this presentation is going to be directed at understanding what is the evidence that the human body can replace lost cells. And so the big question here is, can we repair? And what I mean by repair is, can we replace the cells that are lost because of injury and restore the body to the condition that it was prior to the injury occurring? And so the answer to that question honestly is yes, otherwise we wouldn't be here and I wouldn't be talking. But in order to set this in a more formal scientific manner, what I thought I would do is go over some of the evidence that exists that will convince you that in fact the human body does have the ability to replace lost cells. And in that process, by that process, try to convince you that there is a case to be made for the existence of cells like stem cells. So after I do that, I'm going to look back historically at how adult stem cells in the human body were identified. I'm going to introduce some concepts on how we like to think about how stem cells work. Then I'm going to talk to you about, in addition, so the first part of the talk is going to be directed at adult stem cells. These are the stem cells that repair our bodies. Towards the end of the talk, I'm going to introduce two other classes of stem cells that exist, human stem cells that exist, embryonic stem cells and induced pluripotent stem cells. And I'll tell you what they mean. And I'm going to end with a very, very brief statement that talks about how research on stem cells is regulated in India. I think this is important because there is a lot of research, a lot of work that goes on under this umbrella, and it's potentially very impactful or potentially very harmful to us. So I think it's important for us to know that there is a regulatory framework in place in this country that looks very carefully at what kind of stem cell work can be done and under what conditions. So this is sort of the overview of the talk. I think it's going to take about 20 to 25 minutes to go over all the slides. Please stop me at any time if you don't understand. So let's start with trying to come to a very clearly thought through conclusion that the human body does have the ability to replace cells that are lost. And so this figure here, I think, sort of establishes common ground for all of us. Every one of us growing up has cut ourselves. And we know that at the time when we cut ourselves, there is blood. But if we come back 2 weeks later, we look at the site at which we incurred the cut, we see no signs of the cut. In other words, whatever damage happened at the time when the cut occurred has been completely repaired. The cells that were lost have been completely restored. So this is a commonplace idea, or a commonplace evidence that yes, in fact, the human body has some ability to replace the cells that are lost during injury and to restore it to a condition in which it was prior to the injury having occurred. This is one way to think about it. But let's say we want to ask this question in a slightly more scientific way. What is the capacity that the human body has to replace cells that are lost over the course of our lives? Does every one of our tissues and organs have the same capability that, for example, the skin on the finger has? And what I want to sort of introduce to you now is a series of experiments that were done by a group that is based in Sweden, which I think are really, really cool. So it turns out that as a function of nuclear tests that were done between 1955 and 1963, there was a huge burst of carbon-14 that was released into the atmosphere. This is a radioactive element. The carbon-14 that was released into the atmosphere during that period reacted with oxygen and made carbon dioxide. This carbon dioxide was then subsequently used by plants during photosynthesis. This is a process we don't understand. And naturally, the plants that incorporated this radio-labeled carbon dioxide were then eaten by people. And so this radio-labeled C14 made its way into the cells of the humans who ate these plants. Right? As a consequence of that, there was a very unique phenomenon that took place worldwide. And the phenomenon was that humans who were born between the years 1955 and 1963 all had cells which had a significantly higher level of carbon-14. More importantly, the DNA that existed in their cells were all labeled with this carbon-14 that was released as a function of the nuclear tests that were done during that time. So let's go through exactly how one would estimate this phenomenon. So if you were to monitor the levels of C14, the prediction is that it's been very low from ancient periods to the modern day. And then somewhere between 1955 and 1963, because of all of these nuclear tests, there was a peak. To convince you that this is in fact real, the authors of this study did the following experiment. Now, if you cut a tree, take the cross-section of a tree, what you see are rings. And each one of these rings is the result of cellular deposition that takes place on an annual basis. So now if you start counting rings, you can start putting labels on exactly when these rings were established. So for example, that ring was sort of put in place in 1950. And this ring here, this is a coniferous tree that we're looking at the section of, was sort of put in place in 2000. So what the investigators here did was to actually extract the cellulose from each of these rings and measure the amount of carbon-14 radioactivity. And what they saw was exactly what I said to you, which is to say that the levels of radioactivity in the rings between 1955 and 1963 was significantly higher than rings earlier or rings later. So the idea that emerges is that all the cells that were born in this window of time had a significantly higher level of C14 radioactivity. what the investigators who did this study now wanted to know is if we were to follow the individuals who were born at this time through to their death, say between the years 2003 and 2004, and if you had the ability to estimate what is the level of radioactivity in different tissues in the body, what would you see? This is the question. This is the answer to that question. You have a pointer by any chance? Keep walking. No, look out.
You use the mic. And
No,
the back
I
of
think
your voice is coming out just a little.
Sure.
Yeah.
You should. Yes. All right. So I don't have a pointer, so you're going to have to bear with me while I take you through this. Plot. So again, what is shown in black in this plot is the levels of C14 radioactivity that you would measure in the rings in the tree, or which was in fact a surrogate for the levels of C14 that was in the atmosphere as a function of time. So again, between the years 1955 and 1963, there was a peak in the levels of C14 in the atmosphere because of all of these nuclear tests. Now the red line, let's imagine, is the line, is the time at which a given person was born. Right? Let's say this person was born somewhere between 1960 and 1970. Right? Now let us say that for some reason this person expired between 2003 and 2004, which is exactly what happened in this experiment. All of the tissues that were used for this analysis were used were derived from cases that were submitted to the Department of Forensic Medicine at the Karolinska Institute during this period. Now, say you take the tissues from this person who has passed away in the year 2003, 2004, and ask the question: if I was to look at the cells of the intestine, look at the blood, look at the skin, look at the fat, look at the cells that make up the heart, look at the neurons in the brain, and ask the question, what are the levels of C14 in each of these tissues? What would I see? And what the study found is that if you were to look at the cells of the blood, or you to look at the cells of the skin or the intestinal epithelium, that the levels of radioactivity in these cells was like the levels of radioactivity in the air in the year 2003-2004. But if you measured the levels of radioactivity in tissues like the brain, the cortical neurons of the brain, or you measure the levels of radioactivity in the cardiomyocytes, which are the muscle cells that make up your heart, what you would find is that the levels of radioactivity in these tissues measured in 2003 and 2004 were exactly like the levels of radioactivity in the year 1965, the year this person was born. This is a very important result. Because what this tells you, so in other words, the blood and the intestine, what I haven't put on this is also the skin. So the cells that make up these tissues, the levels of radioactivity in these tissues in the year 2003, 2004, 2005 were comparable to what is the ambient levels of C14 in the atmosphere at this time. But if you measure the levels of radioactivity in the brain, the heart, or the fat, you would find that the levels of radioactivity were very similar to the levels of radioactivity in the air at the time when this person was born. What do you think this experiment means? Well, the interpretation that the people who did this study came to is that the cells that make up the blood, the intestine or the skin, are regenerated very rapidly over the course of the life of the animal, of the person. Whereas the cells that make up the brain, the neurons that constitute the brain, or the cells that make up the heart, are turned over very slowly. As a consequence, the radioactivity that was in them at the time when they were born continues to persist over the lifespan of the animal. Of course, or the person. What is important here is to understand that the overall decline in the levels of radioactivity naturally over this time period is going to be very small, because the half-life of C14 is in excess of 5,000 years. So natural decline in the levels of radioactivity is not going to affect the outcome of this experiment. So what is the conclusion you come to from this experiment? The conclusion that you come to from this experiment is that there are certain tissues in the body that are being very rapidly turned over. Meaning the cells that make up the lining of your intestine, the cells that make up your blood, the cells that make up your skin are being constantly renewed. Whereas the cells that make up other parts of your body, like the brain or the heart, are not being renewed so rapidly. So this is possibly one of the most elegant demonstrations that yes, there is continuous cell loss in the human body, and that the human body has a fundamental mechanism by which it can restore all of the cells that are being lost. Not in the case of every tissue, but certainly in the case of many tissues like the blood, the intestine, and the skin. Right? So I hope the result from this experiment is clear.
During that period of time, like radioactivity can also affect pregnancy in 1970s or 60s when the radioactivity level was high. So it's like during that time it can also affect pregnancy.
Sure.
And then again it also got like a bit normalized with time.
No, so yes, radiation can affect, can cause birth defects, if that is the question that you were asking.
Yeah.
Yes, but in my opinion, the ambient levels of C14, I don't think were sufficiently high to cause those kinds of effects. But the ambient levels of C14 were high enough for you to be able to detect them subsequently in cells that were born at that time. Yeah. Okay.
Just one question.
Yeah.
But when you say that these cells are so high in 1965, they are also got transferred by means of genes to the next generations.
Oh, so what does this mean? So what it means is that if you were born between the years 1955 and 63, that every one of the cells in your body had a certain level of atmospheric C14. Yeah, it's not toxic, but it is above what is ambient, right? It is detected. Let's just put it in those words. Now the question is, these cells can either persist over the course of your lifetime, right? And this includes the cells in your germline, meaning the cells that in your sperm and eggs, which will then give rise to the next generation. All these cells could be lost, meaning because of wear and tear, because of injury, damage that is caused, they could be lost, and they could be replaced by other cells, right? So when you see a complete decline in radioactivity, it implies that the cells that originally incorporated that C14 now no longer exist. But we know that the person in the year 2000, 2003, 2004 had blood, and all of the cells of the blood. So obviously there was some cell that was able to replenish the blood that was lost earlier, right?
So, does this mean that so it's easy for us to prepare ourselves when we injuries and ideas
That's an excellent question. So I think the question she asked is, does that mean that our intestines are going to be better able to cope with the burden of injury than will organs like the brain? Well, the implication is the answer to that question is potentially yes, but of course it depends on the kind of injury and so on and so forth. And we'll come to that. That's a very, very good question because that leads me to the next question. Next slide. Sorry.
Sorry, I have a follow-up question.
Yeah,
Okay.
sure.
I'm trying to figure out, is this the impact of the high C14 in the atmosphere and therefore cells of the people living there? Did that alter DNA of those people?
No. I mean, all of the DNA, all of the chemicals that make up the cells in your body contain carbon. In this case, instead of C12, which is the non-radioactive isotope of carbon, it contains some of the carbon in the cell was replaced with C14. That is all that happened. But the reason I like this experiment is because it sort of gives you a very nice quantitative description of what is the extent to which the human body is turning over its cells over the course of your lifetime. And it's not just an anecdotal piece of evidence, such as, for example, the cut on your skin and how it heals. Right? Okay. So this brings us to what I think is are the two most important questions that I want to sort of discuss with you. And they are the following. What are the cells in the human body that replace the cells that are lost? And how do they work? So to try and address this question, we have to go back in time, again to the turn of the last century. And again, we encounter a phenomenon that we just met, which is the impacts of radioactivity on human existence. So two things happened at the turn of the 20th century. First was the discovery of X-rays. And soon after the discovery of X-rays was the discovery of Becquerel and Curie and others of isotopes, of elements and isotopes that were radioactive. Soon after these elements and radioactivity was discovered, believe it or not, doctors realized very quickly that radioactivity could be used or maybe harnessed to specifically attenuate cancers. And so people started, from the turn of the 20th century, started looking at how they could use radioactivity and sources of radioactivity to specifically target cancers in the body. What they realized when they started experimenting with radioactivity to kill cancers is that one of the consequences of radiation is anemia. In other words, the loss of blood cells. And this is a clinical problem because radiation at very high doses leads to anemia, which can then potentially be lethal to the person who's being exposed to that radioactivity. So there was an awareness in the use of radioactivity specifically for radiotherapy that it has this unfortunate side effect that it kills blood cells. And it can kill blood cells in a way that the person cannot recover. Of course, the other major event that happened in the 20th century that further underlined this phenomenon of radiation-induced anemia was Hiroshima and Nagasaki. And very clear that in 1945, as a consequence of those two atomic explosions, large number of people who were exposed to radioactivity suffered radiation sickness, the loss of blood cells, and lost their lives as a function of it. So one of the things that one of the areas of research that picked up gained a lot of momentum during the middle of the 20th century was research that aimed to understand can we prevent radiation sickness? Is there any way in which we can reverse radiation sickness? In other words, a person exposed to radiation loses blood cells. Is there any way in which we can protect the blood cells in the body from being lost? Is there any way we can rejuvenate the blood in these people so that they don't die from radiation sickness? So in other words, the question that people were asking in the 1930s, 40s and so on, is it possible to protect or repair the blood that is damaged as a function of exposure to radiation? And one of the first things that we do when we encounter a problem in humans that we don't know how to address is we try to recapitulate this phenomenon in the context of an animal model. So we try to see whether animals exposed to the same conditions recapitulate the phenomena, and if they do, then it gives us a way in which we can begin to tease apart how this process happens. And so that's exactly what happened. And in the aftermath of Hiroshima, there were a panel of researchers who began to explore the possibility of using the laboratory mouse to begin to try and understand how to cope with radiation sickness. So if you take a mouse and you expose it to radiation, and by radiation I mean X-rays or gamma rays and so on, then these mice, just like humans, will become anemic. In other words, they will lose blood cells. And what people found when they started doing these experiments, they made two observations which are very important. The first observation that they made is that if you protect the bones of these mice, shield them from the effects of the radiation, or you protect the spleens of these mice, and you then subject them to radiation, they didn't become so sick. In other words, they didn't become anemic and lose their blood cells. And so what this suggested to the people who were doing these experiments is that there's something about the bone, there's something about the spleen that enables the blood cells to be more resistant to the effects of radiation. So the question was, what is it that is accounting for this resilience of the system to radiation? So the next step that happened was the following. People found that if they took bone marrow from mice that had not been exposed to radiation, and they injected this bone marrow back into mice that had been subject to radiation, that now the mice that had been subject to radiation were able to maintain their blood cells. In other words, maintain the complement of cells, or generate the complement of cells in the blood. And these animals did not subsequently succumb to radiation sickness. So, as you might imagine, if you think about the outcome of this experiment, there are two possibilities here. The first possibility is that this bone marrow that I've taken from this healthy mouse and put into this mouse that I've irradiated produces certain protective or reparative factors that then protects the blood cells of the mouse that has been irradiated and doesn't allow them to die or allows them to repair the damage that is caused as a function of radiation. And that is how it protects the system. The other possibility you might imagine is that the bone marrow that I'm putting in from this mouse that is healthy into this mouse that has been irradiated contains some cell that has the ability to regenerate all of the cells of the blood, which are lost in this mouse that has now been irradiated. These are two possibilities. And truth be told, both the possibilities were in contention back in the 1940s, 50s, and 60s. In fact, most people for a while felt that in fact the purpose of this bone marrow or the use of the bone marrow was that it produced protective or reparative factors. And that is what allowed these mice to survive radiation sickness. Right. The data that I'm showing you now is or the experiments that I'm talking to you about now are the experiments that led to this idea that there is a cell in the body that has the ability to make itself and make a whole bunch of other cells. In fact, our blueprint for how stem cells work in human beings is the outcome of these experiments. In fact, more precisely, arguably the most important experiment that was ever done is this experiment by Becker, McCulloch, and Till in 1963. And I'll tell you what that experiment is. And this is the experiment that laid the foundation for this idea that the bone marrow contains a cell that has the ability to make itself and make every other type of blood cell. Once this idea entered the picture, everybody began to think about every other tissue that could repair itself from the same perspective. And this fueled a whole bunch of experiments using the same paradigm that they used for blood to try and isolate those cells. That effort has led to the identification of cells that can be used to grow skin in a dish, etc., etc., etc. And then finally we'll come to the kind of experiment that you talked about. Okay? So let's just flow here. Okay. So to go back one step, take a mouse, you irradiate it, it loses all of its blood cells. You take bone marrow from a mouse that has not been irradiated, you inject this mouse with it, inject its bone with it. Voila, this mouse will now begin to make blood cells, doesn't suffer radiation sickness, doesn't seem to lose all of its blood cells, has a normal complement of blood cells, and is healthy. Question is, how does this happen? And the experiment that was done is a remarkable experiment where what people did was to take the bone marrow from a mouse that was normal. They were able to label the cells of these of the bone marrow and then inject these labeled cells. Let's not go into the details of how the cells were labeled because that's a little complicated. We can discuss it with you later. We were able to label these cells and put it back into this mouse that was irradiated. And what they found was that 10 days later, if you looked at the bone marrow and the spleen of these mice which had received the bone marrow transplant, there were these little nodules that formed. And if you went closely and you looked at what are the cells that make up these nodules, what you noticed is that each nodule contained a whole bunch of different types of blood cells. What was very interesting, there were two interesting observations that came up. First, all of these nodules were made from the cells that you had injected into the mouse. Okay? Cells that you had injected into the mouse gave rise to these nodules that made many different types of blood cells. But the second and the most important conclusion from this experiment was that each nodule came from one cell. In other words, as a function of them being able to label the cells prior to injecting it into this mouse, they were able to follow the fate of each of those cells as they went into the bone marrow and the spleen, seeded these nodules, grew in these nodules, and made different types of blood cells. So the conclusion from this experiment is that one of the reasons why this mouse is able to survive is because in the bone marrow are these cells that have the ability to go to the bone marrow of the mouse into which you injected it, seed the formation of a nodule, and in that nodule generate all of the cells that will ultimately now contribute to the blood. And this was the first evidence that there exists a cell in an adult animal that has the ability to make all of the cells of the tissue of which it is a part. The idea that there is a stem cell. There is a slightly more sophisticated experiment that was done subsequently, which I think highlights the importance of this finding. What was most remarkable is that people found that you could take bone marrow from the mice that had received the transplant, and you could put it back into another mouse that had been irradiated, and you are now able to regenerate the blood in this mouse as well. So this is an even bigger idea. It means that when I take bone marrow and I put it into this irradiated mouse and it makes a nodule, and that nodule contains all of the cells of the blood, some of the cells can be taken, put into another mouse, and it will now again generate all the cells of the blood. So in other words, you have a cell that has the ability to both make itself and make all of the cells in the blood. Yeah.
So it means that they have actually acquired the property of regenerating from the host cell.
No, because if the host cell had this property, it wouldn't become anemic, right?
I mean, it received the bone marrow transplant from a healthy one.
Correct.
The healthy rat donated the bone marrow to
Correct.
the irradiated one.
Correct.
Now you are extracting the sample of the irradiated one
Correct.
and donating this to another irradiated one.
Correct.
The new one is receiving something which was present in the irradiated one.
Correct.
So the irradiated one has acquired it from the
Healthy one. Correct. It's the same cell.
Yeah,
Exactly.
So it's been transferring from.
Absolutely. It has the capacity to be transferred. This is the point. That it can make itself and it can make every other type of cell in the blood. So this is
the same genetic marker is being.
yes, it's the same, effectively the same clonal population, clone, same cell that has made copies of itself and then propagated. Correct. So this cell. So historically, this isn't the hematopoietic stem cell, but this is the approach that was used to subsequently identify the cell that is called a hematopoietic stem cell. Hematopoietic because it can generate all of the cells of the blood. Right? It can generate red blood cells, platelets, all of your B cells, T cells, leukocytes, all of the cells. That same cell. So what's critical is to understand that, as I said before, that these nodules contain many different types of cells, right? So they knew that whatever was seeding these nodules had the ability to make different types of cells. And then they found that they could take these cells and put it back in another mouse, and it would again generate all of this cells, right? Okay.
Bone marrow transplant is done only if there is a match. There is something called that.
Yes.
So how does it, if you can keep doing that,
Yes.
it has to be, everybody has to
Yeah, so this is done in laboratory mice. Let's simplify. Let's just say that these are done in mice that are all that don't have this issue with rejection. But you're right. This
but
is a
the
huge
healthy
problem.
mouse, the bone marrow of the healthy mouse should be similar to that of the
Yes. So these are all. Let's assume for this. That's
The next one also should be similar.
That's correct.
Similar to both the.
That's correct. So
healthy
there's no
ones.
rejection. That's correct. That's correct. Of course, the other issue that you need to consider is that in the process of radiating these mice or exposing them to radiation, you've killed all of the cells in the body that can mount a rejection response as well. So it's slightly more complicated situation. But you're right. Yeah. Okay. So let's take a step back and think through these experiments and understand what can we conclude from all of these experiments that we've done. I think first conclusion, and if you disagree with them, please point this out now. The bone marrow contains a cell that can generate many different types of blood cells. We know this how? Because we've taken the bone marrow from a non-irradiated mouse, put it into an irradiated mouse, and shown that it can make all the blood cells in this irradiated mouse. Okay. The cell has the ability to replenish the blood cells during injury. This is clear. The mouse doesn't become anemic, the mouse does not die. This is the more important thing. This cell can self-renew, meaning it can make itself. And this is important because if it only could make the cells of the blood, then there is no way I could take these cells of the blood, put it into another mouse, and then regenerate all the cells of the blood. So whatever this cell is, this cell can be self-renew. And the last, and this is an extremely important point, which is not clear from the data that I've shown you so far, that the cell is very rare. So when they originally started doing this experiment, they noticed that for 1 in 10,000 cells that they were injecting into this mouse, 1 in 10,000 bone marrow cells that were injecting into this mouse had the ability to form a nodule. So these cells were extremely rare. Right? So this led to this idea, when it comes to the question that you asked, that the bone marrow in mice certainly contains a cell that has the ability to make itself and make all of the cells of the blood, and that this cell is active throughout the course of your life, which is how all of the cells in your blood are being constantly made over. Great. Is this true for a human? Because ultimately the question is, how do humans prepare? This is the subject of the discussion today. And so what's interesting is that even though people knew that there is a cell in the mouse bone marrow that has the ability to regenerate all the cells, it took another 30 years for us to be able to pin that cell down in the context of humans. And the way in which this was done is using the same experimental strategy that was used to identify this cell from the mouse. In other words, You take a mouse, you irradiate it, and this is a special mouse, so that it will not mount a response against the human cells you put into it. Good point. And people began to take fractionated bone marrow cells from humans, put it into the mouse, and ask which of the cells from the human can generate all of the blood cells of the human in the mouse. And believe it or not, this approach ultimately led to the identification of a cell in the human which is exactly like the cell in the mouse. It has the ability to make itself, and it has the ability to make every other type of blood cell in the human. But just to give you an idea of how difficult this process is experimentally, I told you this took 30 years from the experiment that I described in the mouse for it to be accomplished in humans. It involved the birth of two completely new technologies, the ability to make monoclonal antibodies and the ability to sort cells using fluorescence, a technique known as FACS. This technique in itself was awarded a Nobel Prize. So it takes a lot of work to go from something that we knew existed, because people were doing human bone marrow transplants by then, to actually pinning the specific cell in a human that has the same properties as the hematopoietic stem cell in a mouse. So
does it mean that you can reverse also?
Reverse
you can put a cell from the mouse to the...
Yeah, but then you will come across the fundamental problem that this lady has already pointed out very clearly, that you will have rejection issue. Correct. So then this sort of allows us to sort of take a step back and think a little bit more conceptually about what it is that this blood cell or blood stem cell is and what it means. So what I've told you so far is that if you imagine that this is the hematopoietic stem cell in the blood, what this cell has the ability to do fundamentally is to make itself and to make other cells that will then differentiate into the blood cell. Right? So this is what you would call a stem cell that can self-renew, and a cell that can make other types of cells. And for a hematopoietic stem cell, that happens to be all of the cells of the blood. Right. So to close this part of the talk, we started by talking about this very anecdotal, giving you this anecdote about how our bodies can heal with respect to, say, a cut on the skin. And the question was, we all know that our skin has the ability to heal wounds of this kind. And so the question really is, just like the blood has a stem cell that can regenerate the blood, does the skin have stem cells that can regenerate the skin? And the answer to that question is yes. Not one, but there are several different types of stem cells that exist in your skin. There are epidermal stem cells. These are the cells that make up most of your skin. There are hair follicle stem cells. These are the cells that generate the hair that sits in your skin. The epidermal stem cells are the cells that are effectively regenerating the parts of the skin that are between hairs, so to speak. And then in addition to that, you have a population of cells, and this is slightly more controversial. Population of cells called melanocyte stem cells. And these are the stem cells that are responsible for giving your skin the color that it has. Okay. So not one, but yes, 3 different types of stem cells exist in the skin of the body. And these stem cells are in many ways like the cells of the blood, like hematopoietic stem cells. What is important to understand, of course, is that when we think about stem cells in the context of the blood or the skin or the gut or the muscle, that each of these adult stem cells that has the ability to contribute to the maintenance and repair of that tissue is limited in its scope, meaning the stem cell, the hematopoietic stem cell will give rise to blood. It will not give rise to skin, not give rise to muscle. And the reason I'm pointing this out is because at the turn of the century, there was a spate of studies that suggested that the hematopoietic stem cell in the blood has the ability to contribute to many other types of tissues in the human body. There were reports that, for example, this cell could contribute to the lung. And subsequent studies have shown that that is in fact not the case. That these adult stem cells that exist are tissue specific and they generally contribute to the maintenance and repair of the cells within that tissue. So, to summarize, do all adult tissues have stem cells? Many do, but it's not clear that all do. In other words, we don't know, for example, if the different regions of the central nervous system, spinal cord, the different parts of the brain are all equipped with stem cells that have the ability to repair. More importantly, for example, we don't understand whether the cardiomyocytes, the cells that make up the muscles of your heart, have any stem cells that can replenish them. What we do know, of course, is that skeletal muscles have specialized stem cells that can support them, but heart muscle, for example, is open. I mean, it's been a very controversial area, but my understanding is at present there is no definitive evidence that the cells of the heart muscle can be replaced with stem cells.
But the first experiment that we spoke about, the first study that was done based on the people that were born during the time 1955 to 63. From the results of that, shouldn't you be able to say that there are stem cells in the brain and in the spinal cord?
Yeah, fantastic question. Very, very perceptive question. If you look at the data very carefully, if you look at, for example, the levels of radioactivity in the brain or the levels of radioactivity in the heart, there is some room to suggest that there could be some turnover of cells in these respective tissues. But what is important to understand is that when you're sampling the brain, when you're sampling the heart, there is always the possibility that you're taking cells from different tissues. The heart is not just muscle. The heart also contains blood vessels. The heart also contains other types of cells like neurons, and so on and so forth. So one has to be a little bit careful when one is interpreting the data that comes out of that experiment in the context of complex organs, because they are ensembles of tissues. And so what you see could reflect both, of course, turnover in muscle, but it could also reflect turnover in other tissues that are associated with the muscle. So one has to be a little bit careful in the extrapolation of that type of data directly to saying that, because you see a drop in radioactivity in cardiac tissue, it must mean that there is a cardiac stem cell. Right?
Another question that I have is, since we're talking about stem cells being researched, so that this is a very health and wellness sort of question. My question is, doesn't the manifestation of stem cells pose a threat to be more cancerous?
Correct. Absolutely. Absolutely correct. So, because these cells have the ability to self-renew and divide, any perturbation that leads to the loss of control in cell division in these cells will automatically manifest in a cancer. In fact, later when we discuss this idea of what embryonic stem cells are, we will encounter exactly this problem. People imagine, for example, that embryonic stem cells, and I'm sorry I'm jumping ahead because you've asked the question, have this ability to generate every type of tissue in the body. But unfortunately, if you put them into adult bodies, they will almost invariably end up making tumors. So yes, absolutely a very, very important question. Right. Yeah.
I just would like to ask you that when we looked at the cells, there was one where cell which would actually divide further, and that was the cell responsible for the regeneration.
Yeah, there were several such cells, say 1 in 10,000 cells that we put in are like that. Yeah.
So if we actually consider the cancer that is a rapid multiplication of cells, don't you think that was actually controlled because of the rare? Because of 1 in 10,000, because the cell was 1 in 10,000, the chances of cancerous cells was also rare. Do you think this was the responsibility given to that cell? The rareness of the cell be related to the cancerous cells?
No, so I think the point that he was making is that if you have a cell that has this ability to keep making itself indefinitely and making other types of cells, then this cell poses a very real threat. In that if you are unable to control the proliferation of the cell, what you will end up with is a cancer. And the answer to that question is yes. If you're saying, does the frequency of cancers or the susceptibility of the body to cancer relate to the fact that these cells are rare? Arguably, yes. Yes.
Sir, can we just can we do one thing like induce autophagy and then at the same time stem cell therapy? Can we do such thing like at the same time it can reduce the chance of being cancerous, like what should I say, like eliminating aggregations or aggregations at the same time?
Okay, so I think I don't know the precise answer to the question that you're asking because I think it's very general. But I think the direction in which the question is going is absolutely right. I think the question that you're really asking me is how well can we control, how well do we understand how stem cells work, how well are we able to control stem cells so that we can mitigate the risks associated with them. Yeah, so we'll get to that. Let's just go through a few more slides. We'll get to some ideas that may give you a slightly clearer perspective on how to answer the question yourself. Okay, so let's just hold on for a second.
Yeah. You mentioned that a rat could also be injected
No, so yes, so you're asking the same question which I think she asked. So these mice in which these experiments were done were very special mice. These are mice that were genetically engineered so that there was no immune rejection that could occur. So that is what allowed these people doing these experiments to look unambiguously at the fate of the human cells that they were putting into the bone marrow of these mice. Okay, in a normal mouse, you're absolutely right. There was absolutely no chance that the cell that you were introducing could take foot and generate the blood cells simply because there would be an immune response. Which answers the question that you asked, which is matching is critical. Yes, matching is critical. So, alright, so do stem cells, okay, so this is a question that is sort of already been answered, but I thought I would sort of just go over it. Do the same stem cells that contributes towards maintenance also contribute towards injury repair? So in other words, your blood cells are being continuously lost. Of course, if you were to expose to radiation, many more blood cells would be lost, and then your blood cells would have to rejuvenate whatever blood cells are lost. Are they the same cells that are doing all of these things? And the answer to that question is largely yes. But there is some plasticity. And I want to be very clear about what this plasticity means. What this plasticity means is within the context of a tissue, there can be many different types of stem cells, right? And each of these stem cells will only contribute to cells of that tissue. But there could be some plasticity among these cells. For example, a hair follicle stem cell in your skin will make the hair follicle, and that's it. The epidermal stem cells in your skin will make the rest of your skin. But if you were to have a severe injury, then the stem cells that contribute to the hair follicle are a little bit plastic, in that they can also make the other types of cells that make up the skin. So there is some limited plasticity. But the cells that normally contribute to the upkeep of the tissue also contribute to the repair of the tissue in response to severe injury. So now we come to this slightly more mechanistic question, which is how do stem cells work? So what we know in terms of the behavior of stem cells is that they must do two things. They must have the ability to self-renew, meaning make a copy of themselves every time they divide. And of course, they have to have the ability to differentiate. So these are the two things that a stem cell has to do. And so the question really comes down to how do we think about how this is regulated? Sorry, is there a question?
Creepy clock, just gave the time.
Oh, I see that. Sorry, okay, so then the question is how do we think about this, these processes? And so this artist friend of mine, Upsa, who is very kindly illustrated all these pictures, thought that she would try to pictorially represent to you conceptually how we think about how stem cells are regulated. But what is very clear, and this comes to us again from our studies of hematopoietic stem cells, is that there are very precise locations within the body where these stem cells are found. And these locations are extremely important for maintaining the stem cells in their stem-like state. In fact, these locations are so important that what we know is that if we take the stem cell out of that location and put it in a dish and try to get this stem cell to grow in a dish, it doesn't. Right? So this idea that the location at which the stem cell is residing
is when they are not repaired, let's say there is no injury, are they dormant then?
Yes,
Or
exactly. Right. Precisely. In fact, that is the significance of the niche. So the niche is a set of, it describes a microenvironment that keeps the stem cell in a poised state. And that, mechanistically you think that inflammation, the changes in the interactions in that space that are mediated because of signals produced by immune cells, will alter the niche in a manner that then dislodges this cell from that state, allows it to proliferate and make other types of cells. Exactly. Yeah.
So when we have a cut or a skin cut or something, the cells will grow only on that particular area.
Correct.
And will not expand in the other areas.
Correct.
So can we say that because there is an environment provided, it will grow only in that environment?
Exactly.
So when we are doing it on any scaffold or anything, it will just grow there. And when you place that scaffold inside the body, will the cells grow only on that area or will, because of the environment, move around? Or just that because the
That's a complicated question. So, it is possible for us to grow skin in a dish. The skin is very simple because it doesn't have many other same features of skin. For example, there are no sebaceous glands and so on and so forth. But what you can do is you can dislodge this little piece of skin from a dish and you can place it on, say, a bird victim. and this skin will then seamlessly integrate into the surface on which it has been placed. Yes, this does happen.
But then it will stop growing once.
Yes, yes, yes.
This happens with other internal organs also.
Yes.
practice.
Yes, yes. So
There is an internal organ.
absolutely. So cells are contact inhibited generally, unless they're cancerous. Cells will divide when they meet another cell, and there's no other space to grow. They become contact inhibited.
Then there is no question of growing as a cancer cell.
No.
Cells stop.
That's correct. It's a self-limiting process. Yes, correct. Yeah. Sorry.
I have a question.
Yeah.
So how long do these dormant stem cells survive? Consider they get no stimulus or anything to convert into another cell. How long can they actually survive?
Well,
Before they die?
if it's a stem cell, indefinitely, because it can self-renew.
Okay. So how long is this?
No, but you're right. The
cells?
point that you're making is, are there conditions under which stem cells become depleted?
Yeah.
Sure. I mean, you could argue that, as a function of age, our ability to heal, let us say, is diminishing. Could that be accounted for example, by depletion of stem cells? Absolutely. The stem cell itself can be targeted and it can die. For example, radiation does exactly that. Radiation eliminates the population of hematopoietic stem cells in the body as a consequence of which you see anemia.
Okay, so consider one that stem cell can't divide. Or how long does it? And my question is, how long can that particular stem cell stay dormant without undergoing division? Can it indefinitely?
Indefinitely. There is no logical reason to suggest that unless there is a change to the niche, there is no reason to imagine that that stem cell will lose its stemness or be pushed from that stage to any other.
I want to just interrupt to say something. So we're kind of past time. You can continue to speak to Arjun if we're going to have a little tea and thing here, like a
Yeah.
party.
So let me just wrap up in 2 minutes.
Yeah. So Arjun, talk about, if you have any more questions, please.
Yeah, let's carry on the discussion after.
Yeah.
Fine.
So
Sorry. Sorry.
so there is a time when the telomeres will be too short, the cells won't be able to divide.
That's correct.
So at that time,
Yeah, but it's not clear to me that applies to a stem cell. Most cells, when they divide, will obey what you call the Hayflick limit, which is to say after 50 rounds of division, because of irreversible shortening of the telomeres, they will stop dividing. It is not clear that the stem cell has that property. The stem cell has the ability to maintain its telomeres and divide indefinitely. So that's it. Right, so let me just quickly end, because I think we're running out of time. But the concept of a stem cell, so the question really is, are adult stem cells the only human stem cells we know? The answer to that question is no. There are other types of human stem cells, and these are arguably much more powerful. Remember that the concept of a stem cell is very simple. It's a cell that can self-renew, or it's a cell that can differentiate to make other types of cells. And as all of you know, each of us essentially started as a single cell during development. And then we reached a stage when there were about 200 cells, and there was this outer sheet, and then there were these inner cells. And then this implants into the uterus as a function of implantation, and this happens in about, I think, a week or so. You produce a hormone which you then detect in a pregnancy test, while this embryo then develops to make a human being. So this is what happens. And what is interesting is that if you look at the cells that make up this 200 cell structure, specifically these inner cells, structures of cells that are called the inner cell mats, these cells can make every cell in your body. These cells, if you put them in a dish, have the ability to continue to make themselves. And we know, because we can take a cell and differentiate it, that this cell, based on what it does in the body, that this cell has the ability to make every other type of cell in the body. Right? So these are not like adult stem cells. Adult stem cells are also cells that can make themselves indefinitely and make other cells, but they're very limited in the repertoire that they can make. Right? These cells are completely unlimited in the repertoire that they can make. These cells can make every cell in the body. Right? And so these are referred to as embryonic stem cells. This is another class of stem cells from the human. And the last, and this is a slightly more recent idea, it was awarded the Nobel Prize in 2012. There is a technology now that allows us to take any cell in the body virtually, and as a function of expressing specific groups of transcription factors in them, we don't have to go into what transcription factors are, you have the ability to convert these cells into a cell which is very much like an embryonic stem cell. Right? And so this is arguably the most important and potentially useful therapeutic population of stem cells that can be used to generate cells that can then aid and augment the process of repair in the body. So adult stem cells can be augmented, or in the case of tissues which don't have any adult stem cells, these tissues as well can be repaired with assistance from embryonic stem cells or induced pluripotent stem cells. So this is the idea. So I'm going to end now, and I just want to tell you that all of the stem cell research that we do in the country, this is important because of what we read about in the papers every day. All of the stem cell research in the country is regulated by the government. There is a National Apex Committee for Stem Cell Research and Therapy, and this committee has laid down very clear guidelines for any institution in this country that wants to actively work on stem cells. If any of you are interested into what are the kinds of rules and regulations that exist in the country about working on stem cells, you can visit their website. And I thought I would end with a brief statement which is on the website of the NAC, which should set in perspective for you all of the claims that are made about stem cell therapy in this country. As per the National Guidelines for Stem Cell Research 2017, at present, there are no approved indications for stem cell therapy other than hematopoietic stem cell transplantation. And this is exactly what we were discussing earlier, for hematological disorders. Accordingly, all stem cell therapies other than the above shall be treated as investigational and may be conducted only in the form of clinical trials after obtaining necessary regulatory approvals. Use of stem cells for any other purpose outside the domain of clinical trials will be considered unethical and hence not permissible. So one of the questions that, for example, we get asked as scientists who work on stem cells is, this is an advertised stem cell therapy. Is this something that we should consider? And it's very difficult for us to comment on that simply because we don't know sufficient details about whatever it is, this therapy that is being offered. So the simplest solution to the problem of trying to understand whether a given stem cell therapy is applicable or not is to first research about it online, or more importantly, ask other medical practitioners who are qualified whether they approve of such a therapy or not before you decide to engage in that therapy per se. So I'll end with that and then we can carry the discussion.
Arjun, do we have time for one last question? We have one question.
Yeah, sure.
This entire industry about harvesting the umbilical
I
cord.
can't hear you.
The umbilical cord.
Yes.
There's this entire.
Yes.
So is that the embryonic stem cell?
No. Very, very good. Fantastic question. So the question that has been asked to me is, what is this cord blood business? Stating it in technical terms. Yeah. Okay. So it turns out that, none of you asked me the question, where do these adult hematopoietic stem cells come from? And it turns out that these adult hematopoietic stem cells come from the embryo, where there are hematopoietic stem cells, blood that arises in different locations in the human body during development. One of the places where it arises is the placenta. And from the placenta it moves to the liver, from the liver it ultimately moves to the bone marrow, which is where the adult hematopoietic stem cell sits. So the reason why cord blood is so interesting is because it contains hematopoietic stem cell progeny. There is reason to believe that the hematopoietic stem cells that you can derive from cord blood could be slightly better at engraftment and at a long-term self-renewal than adult hematopoietic stem cells. But the limitation is that the number of such cells in cord blood are very few. So one of the reasons why this business has grown is simply because that tissue could be a reservoir for hematopoietic stem cells should you need it later in life. So does that answer your question?
Thank you, Arjun. That was